forces and motion. It covers pressure, how forces change shapes, distance, speed and acceleration, and forces and motion. First, pressure. Let's remind ourselves what pressure actually is. Pressure is the effect of a force acting on a surface. The pressure on a surface depends on the force and the area of the surface the force is acting on. This clip explains how.
In extreme close-up, you can see the cutting edge of a knife isn't totally sharp. It's a very small surface. A sharp knife has a much smaller cutting surface than a blunt one. When you cut, you apply a pushing force to this surface. The larger the surface, the harder you have to push to cut. It's the pressure of the knife on the apple which makes it cut. This pressure depends on both the pushing force and the area of the cutting edge. If you stand on something squashy like sand, you can easily see the pressure caused by your weight acting over the area of the sole of your shoes. It's the pressure which produces footprints. I weigh the same, but my footprint is deeper wearing this than this. The pressure depends on the area of the sole of the shoe. So, as my weight stays the same, if I double the area of the sole of my shoes, I should halve the pressure. As the area gets bigger, the pressure gets smaller. So, the footprints from my red shoes are deeper than the green ones.
So the two key points are that the greater the force, the greater the pressure, but the greater the area, the smaller the pressure, because the same force is spread over a large area. There's a formula for this. It's pressure equals force divided by area. That's P equals N for newtons divided by m squared, that's square meters. So the unit of pressure is newtons per square meter, or pascals. Can you think of things that work better by spreading a force over a larger area or by concentrating it in a smaller area? Skis and snowshoes reduce the pressure on the snow by spreading your weight over a larger area to stop you sinking. Some animals have large or webbed feet to stop them sinking in mud or sand. And caterpillar tracks stop heavy vehicles sinking into the ground. On the other hand, a drawing pin has a large area to push your thumb on and a much smaller area at the point. That means a much greater pressure is applied at the point than you can apply with your thumb. Hydraulics is something else that makes use of the way pressure changes with area. Liquid can't be compressed easily because the particles in a liquid are so close together. Because of that, pressure on a trapped liquid is transmitted through the liquid. Here's a diagram of a hydraulic car jack. On one side of the hydraulic jack, the car exerts a large force over a large area platform and exerts a certain pressure on the liquid. The liquid is not compressed, so that same pressure, that's force per square metre, is transmitted through the liquid to the piston on the other side of the jack. Here, the same pressure can be held back by a much smaller area of piston. That means it only needs a much smaller force to hold the car. Next, pressure in gases. Watch the next clip and try and work out the relationship between the pressure and the volume of a gas.
These cylinders are a diver's life support system. Inside each one is a phone box full of air, compressed down so much that the cylinders actually get heavier as they're filled. The air inside weighs as much as 3 bags of sugar. Let out all at once, that air would blow a diver's head off. So a mouthpiece releases it slowly, regulating the pressure to keep the diver alive for up to an hour underwater. Divers know that everything depends on their equipment working perfectly, so they check and double-check it on the surface. Down below, it could be too late. It's going up and down that can cause problems. Divers must wait for their bodies to adapt to the change in pressure on their skin and inside their heads. As Charlotte dives deeper, she can feel her body being squeezed. That's pressure. It happens because the weight of the water in a column directly above is pressing on her skin.
You can see that as I descend with this empty plastic bottle, the bottle is crushed as the air is compressed inside.
The air is still inside the bottle. It's just being compressed into a smaller space by the force of water weighing down from above. The plastic buckles because it's not strong enough to withstand that force. This glass jar is open at the bottom. As the pressure increases, it forces water into the jar, reducing the surface area of the air trapped at the top.
In fact, as the pressure on the pocket of air in the cylinder from the water above increases, the volume of the air gets smaller.
The pocket of air shrinks, even though no air escapes.
The opposite is also true. When the pressure on the gas in this fizzy water is released, its volume increases, and out it rushes. We saw that, unlike a liquid, a gas, such as air, can be compressed, and the volume it occupies gets smaller. So if the pressure on a gas increases, its volume decreases, and if the pressure decreases, its volume increases. Another way of saying that is that the pressure and volume in a gas are inversely proportional. There's a formula for this, which says that for any gas, pressure times volume is constant, assuming the temperature stays the same. This is Boyle's law. That's the end of the section on pressure. This section is about how forces can change shapes.
Watch what happens as I sit down. Let's look at that again. At first, my weight is a bigger force than the upward force of the cushion springs, so I go down. But the more squashed the springs get, the more they push back. Eventually, the force pushing back equals my weight. The forces in each direction balance, and I stay put. It's called equilibrium.
With a bungee jump, as the elastic stretches, the force in it increases until it's big enough to stop the person falling. So a force can compress a spring, but the more the spring is compressed, the greater the force it exerts in the opposite direction until it balances the force that's compressing it. A force can also stretch a bungee elastic, but the more the elastic is stretched, the greater the force it exerts in the opposite direction until it balances the force that's stretching it. If you apply a force to a spring, it will compress, but only by a certain amount. That's because the spring exerts a tension, which acts in the opposite direction to the force that's compressing it until the two forces balance. Increasing the force compresses the spring further. This increases the tension in the spring until, yet again, it balances the force compressing the spring. This continues until the spring is completely closed up and can compress no further. The same applies if a force stretches the spring. The spring extends until the tension in the spring balances the force on the spring. Increasing the force extends the spring further, which increases the tension in the spring until, yet again, it balances the force on the spring. This continues until the elastic limit of the spring is reached, when the tension in the spring can no longer balance the force pulling on it, and the spring becomes overstretched. A graph of the force on the spring against the length of the spring is a straight line. This means that the compression of a spring is proportional to the force compressing it. The extension of a spring is also proportional to the force extending it. This relationship is known as Hooke's law. As long as its elastic limit is not exceeded, when a spring is compressed or extended, it will return to its original shape. Materials that return to their original shape in this way are called elastic materials. And that applies not just to a piece of elastic, but any material that retains its shape, like rubber or a metal spring, or lycra clothes. If these materials are stretched beyond their elastic limit, they become permanently deformed and no longer return to their original shape. The elastic properties of springs are used in mattresses, kitchen scales, and suspension systems. Other materials such as wood and concrete are slightly elastic, so when they're used in buildings, they flex slightly in response to atmospheric disturbances and the Earth's movement. Plastic materials also change their shape when a force is applied, but they don't go back to their original shape once the force is removed. Clay is a plastic material. It's important to be clear about the difference between plastic and elastic materials. That's the end of the section on how forces change shapes. This section is about distance, speed, and acceleration. Before we start, let's be sure exactly what we mean by speed and how to calculate it.
I think we should look at exactly what speed is. Now, our speed tells us the distance we've travelled in a certain time. And the faster the speed, the more ground we cover each second. So, to be able to work out our speed, we need to know the distance we've travelled and the time taken to cover that distance.
But how can you tell if a car's speeding? Would you just guess?
Oh, no, we don't guess. I have several methods open to me. I have a speed gun, I have fixed cameras at the side of the road, and we have a time and distance computer.
To calculate the speed of a car, Tom needs two measurements: a distance the car has travelled and the time it took to cover that distance. Tom can use the computer to measure the distance between these markings on the road and the markings under the shadow of the bridge. And then all he has to do is time how long it takes a car to travel between the two marks. Dividing the distance by the time gives him the car's speed.
We've put in 105, which is the distance measurement, and now on this side we're going to use the stopwatch side of it, and we're going to time the vehicles travelling between the white paint marks and the bridge.
Black car in the outside lane. I don't think it's going that fast. Let's see.
No, nor do I.
Here we go.
The shadow, that's it.
Now, to get the speed, all I have to do is divide the distance by the time the car takes to cover it. Luckily, the computer does that for me.
49.93.
Oh, you were lucky.
Just within the limit by 0.7 of a mile an hour.
You were lucky.
Another way Tom can measure speed is by using roadside cameras, which are triggered by cars going too fast, and the double flash and the markings on the road are a clue to how they work.
Each site has calibration marks laid on the road surface that are 2 metres apart. Now, when a car comes along and triggers the camera and has a photograph taken, it automatically takes a second photograph half a second later. Now, all we do is put our finger on the mark there where the back wheel is, move on to the second photograph, and count how many squares the vehicle has travelled in that half second.
OK, so that's 1, 2, 3, 4, 5. Now, they're 2 metres apart, is that right? So that means in half a second that car has travelled 10 metres.
That's correct. And then we look on the chart behind us and we see that metres travelled 10 and half a second equates to 44.7 miles an hour. Now that's nearly 45 miles an hour, and we will send this motorist a notice of intended prosecution.
This man means business.
So speed is distance divided by time. The unit of speed is metres per second, kilometres per hour, or miles per hour, depending on the units of distance and time being used. If speed equals distance divided by time, and you know any two of these values, you can work out the remaining one. Distance equals speed multiplied by time, and time equals distance divided by speed. If something doesn't travel at a constant speed, it must be getting faster and faster or going slower and slower. Accelerating is the word for getting faster and faster, and decelerating is the word for getting slower and slower. Acceleration, or deceleration, is the rate at which the speed is changing. There's more about distance, speed and acceleration in the higher tier programme. That's the end of distance, speed and acceleration. This section is about forces and motion. If an object is at rest on a table or hanging from a thread, it will stay where it is. That sounds obvious, but the reason is because the forces acting on it are balanced. The weight of the book acting downwards is balanced by the equal and opposite force of the table pushing upwards. The weight of the ball acting downwards is balanced by the equal and opposite force of the thread pulling upwards. This is part of Newton's first law of motion. This says that if the forces working on an object are balanced, it will remain stationary or will continue to move in the same direction. That second part is more difficult to believe. We know that a toy car rolled along the floor doesn't continue to move forever. So is Newton wrong? Think about it as you watch this clip about the space shuttle.
Small adjustments to the height of the orbit and the position in the orbit can be made using small thrusters. To the astronauts, free falling with the ship, it seems that when a thruster is fired, the shuttle moves off in the opposite direction and continues moving until an opposite thruster is fired.
Okay, rod release, ready, green, 33. Helmet lights on, helmet lights are on, and your front.
To get to the satellite and to make small changes to it, the astronaut had the MMU, the Manned Manoeuvring Unit. "300 metres can be a long way in space. The MMU is manoeuvred by very tiny thrusters, but in the same way as the shuttle.
Okay, Pink is sitting out there at about 140 feet at this time. Sure.
He had no sensation of hurtling round in orbit. He felt as if he was floating weightless and using the MMU to move around. Still, the astronaut had to use the thrusters gently. Too much, or in the wrong direction, and he would have pushed himself dangerously off course. The idea was for him to match the spin of the satellite, then clamp on and use the thrusters in the opposite direction
and so stop the satellite spinning. At least that was the theory. In fact, because his mass was low and the much more massive satellite was turning quite quickly, he was knocked away.
You might have noticed that, floating in space, the shuttle and the astronaut did keep moving until they used their thruster rocket to stop the movement. Also, we saw that the satellite would keep on spinning until the astronaut managed to stop it. So Newton was right. On Earth, there are many forces acting on an object. Friction is a force that opposes motion and reduces the speed of a moving object. Friction takes place between the objects and a surface. The rougher the surface, the greater the friction. Friction increases with the weight of the object. Air resistance, also called drag, is the way that air resists an object that's trying to move through it. The shape of an object affects its air resistance. The more streamlined the shape, the lower its air resistance. Contact forces are when two objects are in contact and exert an equal and opposite force on each other. Gravity is the force on any mass pulling it towards the centre of the Earth. The force of gravity on an object is its weight. On Earth, gravity exerts a force of around 10 newtons on a 1 kilogram mass. Gravity is a field force. It works without being in contact with the object. In your exam, there's a proper way to represent forces. You use an arrow pointing in the direction in which the force is acting. The length of the arrow indicates the size of the force, while the head of the arrow indicates its direction. For the object to stay still or to keep moving at constant speed, it needs all the forces on it to be balanced. What are the forces on this stationary car? There's the force of gravity acting downwards on the mass of the car, its weight, which is balanced by the upthrust force of the road surface on the car tyres, which pass through the car's suspension to hold up the mass of the car. The car is now moving at a constant speed along a flat and level road. What are the balance forces on the car now? You should have got something like this. There's still the force of gravity acting downwards on the mass of the car, balanced by the upthrust force of the road. But now the car is moving at constant speed, there's also the forward driving force provided by the engine passing through the wheels and tyres to the road. This is balanced by the frictional forces in the turning wheels and where the tyres meet the road, as well as the drag from air resistance, both trying to slow the car down. If there were no drag or friction and the road stayed flat and level, what would happen if the driver switched off the car engine? According to Newton's first law of motion, if there were no drag or friction and the road stayed flat and level, the car would continue rolling at the same speed, forever, just like a space astronaut. What if the forces on an object are unbalanced? If the forces acting on an object are unbalanced, the object will start to move and speed up or slow down and stop. Watch the next clip to see how much force is needed to get an object moving and how much force is needed to stop it.
This is an old-fashioned horse-drawn dray, and it's still used to deliver beer in London. It has a mass of 1,500 kilograms and normally takes 2 strapping shire horses to pull it around. But today, it's just going to be Jamie.
Ready, Jamie? Go!
Now, if I convert the reading on the forceometer into metric units, I can see that Jamie needed a force of 4.5 kilonewtons. That's 4,500 newtons to start the carriage moving, but he doesn't seem to need as much to keep it moving.
Stop!
But how much force will he need to stop it?
Jamie, awesome or what? Amazing. Now, you obviously had to exert an awful lot of force to get the carriage started.
It's always difficult starting something like this because you have to overcome friction and unbalance the forces, but once it's actually moving, it's just a constant force to keep it moving.
So to get the dray to move, Jamie had to unbalance the forces acting on it. As it starts to move, it's accelerating, or rather being accelerated by Jamie pulling with a force greater than friction. But once the carriage was moving, it became a lot easier because all he had to do to keep a constant speed was to balance the forces acting on the dray. But to slow down and stop the carriage once again required unbalanced forces.
You need an unbalanced force to make something accelerate or decelerate. In fact, if you double the force, you double the acceleration. If you double the load, that's the mass, you halve the acceleration. The bigger the unbalanced force, the bigger the acceleration. The bigger the mass, the smaller the acceleration. Let's summarise. Forces have a size and a direction. Forces acting on an object can change its shape, make it start or stop moving, make it speed up or slow down, or change its direction. The bigger the force, the bigger the change. The bigger the mass, the bigger the force needed to bring about a change. Static objects can exert a force. If an object is either at rest or moving at a constant speed, then the forces acting on it are balanced. If an object starts to move, speed up or slow down, the forces acting on it are unbalanced. There's more about forces and motion in the higher tier programme.